So we're talking about property tables commonly found in the back of a thermodynamics textbook. And if you look at the back of any book, you'll see many different tables. I have with me here a number of different books that I'm sure some of you may be using. In the course that I'm currently teaching, I'm using a book by Cengel and Boles. And if you look at the back of that book, there are a number of different tables, both in SI as well as in British units. I'll mainly be using SI throughout this course, but there you'll find things such as saturated water temperature table, saturated water pressure table, compressed liquid water, TS diagram for water, Mollier diagram for water. So that's what is in the back of Cengel and Boles. Another book authored by Borgnac and Sontag. This one is Fundamentals of Thermodynamics. Again, single state properties in SI at the back of the book, thermodynamic tables, so properties of water, properties of ammonia, carbon dioxide. Here they have R410A as well as R134A, properties of nitrogen, methane. So this is quite typical. And then another book that is quite common, the one by Moran and Shapiro. You go to the back of that book, and again, there are a wide variety of tables. Here they have saturated refrigerant 22, so liquid vapor temperature table, saturated water temperature table, superheated water, saturated water, and the saturated water, that'd be the liquid vapor, both temperature as well as pressure table. So you'll find any book that you look at will have these tables at the back, and depending on the authors, you'll have different liquids that are presented. But what we're going to talk about here is both steam or water as well as R134A. So the tables are presented in a manner that enable you to be able to solve the problems, but it's important for you to understand which table pertains to a certain type of problem that you might be looking at. So to begin with, if you're at a given pressure, so the pressure is fixed, so if you're at a given pressure, so maybe it's your local atmospheric pressure, it might be 10 megapascals, something like that, but the temperature at which the substance changes phase, that is, goes from a liquid to vapor, that occurs at the saturation temperature, which is called Tsat. And if you look in the back of your thermodynamics book, you will find tables that pertain to that situation. So remember, we said we're at a fixed pressure, so you would want to look in the back of your book and find saturated water and what are called the pressure tables. And if you're dealing with R134A, that would be saturated R134A, and again the pressure table. So that's one set of tables that you'll be using, so I'll star that. Another form is if you have your temperature fixed, so here you're talking about the saturation pressure at which you undergo a phase change. So if you have the temperature fixed, then you'd be looking at the saturation pressure. So again, the tables, there would be a table for saturated water. However, we would call these the temperature table. And you could have saturated R134A, and again, you'd be looking at your temperature table. So you may want to look in the back of your thermodynamics book and look for these tables. So for saturated water, first of all, we talked about the pressure tables. And what that will list will be a different number of properties that I'll talk about in a moment. But on the left-hand most column is going to be a column with pressure. And so you will see your different pressures, and then for each particular pressure there will be a saturation temperature. That is the temperature at which you go through the phase change process. And then you'll have specific properties that you would use for your problems. And in this case, in this table, there's specific volume, internal energy, enthalpy, and entropy. So those are a couple of the tables that you will be using, and those only pertain to when you're going through the phase change process itself. They don't apply where you only have liquid, that's the compressed liquid region, and they do not apply where you have superheated vapor. You use different tables for those regions, so be aware of that. So these two tables, the ones that I just referred to, be it the pressure table or the temperature table, they present the following data. So those are the different things that are presented in either the pressure table or the temperature table in the two-phase region. And what you'll find is you'll have specific volume, internal energy, enthalpy, and entropy. And the nomenclature for each of those, the subscripts, either an F or a G, we'll talk about it later, but F would pertain to the saturated liquid and the G would pertain to the saturated vapor point. If you recall, we talked about that as being the two extremes in your two-phase region. Now, if you're to the left of the saturated region, you are in what is referred to as being the compressed liquid region. And so there you have not gone into a phase change process yet. So the compressed liquid region. And in the back of a book, you'll find tables that say things like compressed liquid water. So looking in the tables that I have here, they're referred to as being compressed liquid water, and there the properties are presented at different pressures. So we have 5 MPa, 10 MPa, 15 MPa. And they'll show saturation temperature and then increasing temperature on the left-hand side. So that's what the tables are plotted against. So these are plotted for a fixed pressure. And when you look in the table, you'll see temperature, specific volume, and that will be denoted by little v, units there are meters cubed per kilogram. Internal energy, that's little u, and that is kilojoules per kilogram. Enthalpy, and that is H, kilojoules per kilogram. And finally, entropy. And that is denoted by little s, and that's kilojoules per kilogram Kelvin. So those are the properties that you'll find in the compressed liquid region tables. Now, if we're to the right of the two-phase region, then we would be in what is referred to as being the superheated vapor region. So in this region, what has happened is all of the liquid has boiled. It's gone into vapor phase, and then we've increased the temperature beyond the saturation temperature. So we're in the superheated vapor region. And if you look in your textbook, you'll find probably You might have one for superheated water. And you might have one for superheated refrigerants, whatever you're using in your book. In the case of Cengel and Boles, they use R134A. And here, the way that the data is presented, if you're looking now in your superheated vapor, so here they call it superheated water, and what you'll find, again, you'll have them presented at different pressures, and for each pressure, you'll start at the saturation temperature, so the point where you go through the phase change process, and then temperature will go up from that point. And so you'll have different pressures for the superheated water tables. And so what is being presented then is temperature, specific volume, and that's going to be little v in units of meters cubed per kilogram. Just like before, internal energy, and that will be symbol little u, kilojoules per kilogram. You have enthalpy, and that is little h, and that is kilojoules per kilogram. And finally, entropy, and that is S. Notice entropy is different from the others in terms of the units. It's kilojoules per kilogram Kelvin. Okay, so those are the tables that you'll be using. Now, there is also similar data. I'll put that on the next page, but it's also presented in diagram form. And additionally, if you have access to the internet during your work, you can find a lot of this information on the internet. The thermodynamic table data you can get there from many different websites. However, just be aware that sometimes when you're solving problems, if you don't have access to that, for example, in an exam situation, it's good to know how to use these tables because you're doing a lot of interpolation. So what I would recommend while you're doing your homework, I would recommend that you use the tables, that you're comfortable with them and you know how to use them. But the diagrams that you will find in the book, there are diagrams for water, and typically you'll find a TS diagram. These diagrams are not as accurate, remember I mentioned earlier, as the tables. And you also have an enthalpy versus entropy, and that is referred to as being the Mollier diagram. And sometimes with certain processes, you can actually go through the process fairly quickly with the Mollier diagram, especially if you're dealing with the case of constant entropy. You can just move up and down in the diagram. However, again, you have to read the charts. It's good to have a ruler if you're doing that so that you get accurate results. And depending on what type of refrigerant you may be using, for refrigerant, R134A, in the case of Cengel and Boles, he has a pH diagram. You may have different diagrams in the particular book that you're using. So these are the tables and diagrams that we'll be using while applying the first law as well as the second law to analyze any kind of system that we will look at within this course.